Thank you. Thank you for the invitation and for you to be still here for the last talk of this really nice week. So in here we'll present this work that I did with my colleagues from the University of Chile, Felipe Tobar and Joaquin Fombona. And so I'm going to talk about Barycenters for optimal weak mass transport. So first of all, I will talk a little bit about optimal weak mass transport because we haven't heard of it during this week, and maybe just give you some intuition about this subject. So yeah, first of all, as you all know, I guess in here, we have the Manche problem with this really nice figure adapted from the Tor's book. So where we have two probability measures in here with density, and we look for a map, an optimal map, that will move the measure mu to the measure nu. So in all my talk, I will talk about, consider probability measures that live in the Euclidean space of dimension d, and that are well-behaved, meaning that are moments of order 2. Because I will explicitly use actually the Wasserstein distance 2, so with an squared Euclidean cost. So in here you have the Manche problem that you all know also. We are looking for a map that push the measure mu toward the measure nu, with the push forward operator in here. So this problem, as you all know again, can be also relaxed with the counter-reach formulation. Okay, so we don't always have a map actually that can push, for example, in here, a Dirac onto two Diracs. Okay, so a measure mu supported on x1 and a measure nu supported on y1 and y2. So in here we have the counter-reach problem, which will aims to find this time not a map but a transport plan, meaning a probability measure on the space RD times RD, that will minimize the global cost of transporting the mass of mu onto the mass of nu. Now that we have this in mind, we can also write it like the correspondence between the two problems. If we have a nice measure mu, meaning that is absolutely continuous in here, we know that in this case actually there exists T star and P star that will be optimal in respectively the Manche and counter-reach problem, and we will be able to write this relationship between P stars and T stars. So the first line is the constraint on the Manche problem, the push-forward constraint, and the second line is a constraint on the counter-reach problem, meaning that P star needs to have marginals mu and nu. Okay, and in this case we can actually write the P star push-forward. The P star, sorry, is supported on the graph of the measurable function T star. Okay. So this is well known, and we have this relationship actually that P star we can disaggregate it, with respect to the first marginal, and we have this measure depending on x, and in this case with this disintegration actually T stars is written as in integral, which is just the conditional expectation of y, knowing x is equal to small x. And in here, of course, the conditional expectation is taken with respect to the optimal transport plan in the counter-reach problem. Okay? So why I'm talking about this? Actually, this nice setting, this works, this formulation works because in this case, actually, the disintegration measure is only the Dirac in the position of T star of x. Okay? And you recover at T stars of x. But actually, this formulation, as I said, which is just the conditional expectation of y knowing x, can be defined for any transport plan with marginal mu and nu. Okay? And this is called the barycentric projection, which has nothing to do with the barycenter, but it's just, it has this name because of the way it is written, meaning that it's written as an expectation, an average. Okay, so here we have equivalent formulation, and we define with this S mu of nu the barycentric projection. And the idea actually was to work with this kind of maps instead of the Mange map, and to see what happens if we change the classical Mange map that we know that does not always exist, which is kind of a bummer, and to use this kind of map that are defined through an optimal transport plan. And the nice way to do it, actually, to see the optimal weak mass transport that has been introduced by Gosselin, Roberto, Sampson, and Tetali in 2017. And so in here, you have what they call the optimal weak transport. They actually define it for more general cost, barycentric cost, but in here I will just use the squared Euclidean cost. So in here you have two priority measures, mu and nu, and you have the infimum. You look for the infimum of on all the transport plan with marginal mu and nu, such that globally we want to minimize the distance between a point x in the support of mu and a conditional expectation of y with respect to this point x. Okay, so there is a notion of locality inside the global problem of transport. So of course, this you can write it as expectations, as an expectation of the random variable x minus the conditional expectation of y knowing x. Okay, and in here you recognize the barycentric projections that I defined just in the slide before. Now some intuition about this object. So in classical optimal transport, if I have two priority measures, mu and nu, so mu is supported on the red dots with weights 1/2, everyone, and mu is supported on the blue dots. So in classical optimal transport, you will send this mass toward this one, and this mass toward this one. Okay, this is the optimal way of moving the mass in the classical setting. In optimal weak mass transport, it is not. The optimal way will be to move most of the mass on the points that is close to it, and a little bit of the mass more far away. Okay. And so this actually can be understood. Maybe, well, you have this notion of averaging that appears in here, but this can be understood thanks to a nice characterization of actually through convex ordering. So I'm going to talk about that and why it's interesting to also see these tools. So just so you know, this is not symmetric. So this is an important point. It's not a distance, but still. So here you have the works of Gosselin and Juillet and also Hulubakov, Eragas, and his co-authors. That are really nice work to begin with optimal weak mass transport if you're interested in it. They are really well written paper and with a lot of theoretical results. So first of all, the optimal plan in this case is always unique. You don't need regularity on your measure in order to have a uniqueness of the optimal transport plan. Second, I was talking about this characterization in particular. Optimal weak mass transport can be written in terms of classical Wasserstein 2 distance with this relation. So two measures are in convex order, okay, in here eta and nu. If for any convex function phi, you have that the integral of phi against eta is smaller than the interval of phi against nu, okay? And in this space of measure, the space of measures that are smaller than you are trying to find the eta that will reach this minimum, and you will recover actually the optimal weak mass transport. So what you have in mind is that you have two measures, mu and nu, and you have mu in here, and you are trying to find an eta measure that is smaller in convex order than nu, and it close in the classical way, in the classical sense, to the Wasserstein distance. Just to have in mind, to have some intuition also on the convex ordering, if you take phi, the function x or minus x, you will have that eta and nu must have the same mean. Okay? And also if you take you will have that the variance of eta must be smaller than the variance of nu. Okay, so there is a notion of concentration. Okay, so this I'm gonna maybe write it just to have in mind this characterization for later maybe. So the weak center is on eta smaller than in convex order than nu of the 2 Wasserstein distance squared. And actually, this eta star, which is uniquely defined, can be written as a push forward of the measure mu through the barycentric projection. Of course, the barycentric projection, which is associated with the optimal plane in this problem, okay, which is the mean on P with marginal mu and nu, the expectation of x minus expectation of y running x. Okay. P. Okay, so now we have all of the tools and all of the relationship between the optimal mass the weak transport in this formulation with respect to the Wasserstein distance and the formulation with respect to the optimal transport plane. And for those of you who are familiar with martingale coupling, actually, eta being smaller than nu is equivalent to saying that you have the conditional expectation of y knowing there exists a coupling such that the conditional expectation of y knowing x is equal to x, okay, for almost every eta. X, sorry. Okay. So now we have an idea of what is optimal weak mass transport. I will present some example in here. So in here I have two priority measures, mu and nu, supported on these points, so on xi and yj, with equal mass. So when I'm computing actually a barycentric projection with respect to an optimal plane in the classical case, I will have something that is close to nu, but it's not exactly nu in this case because actually a merge map doesn't exist. Okay, so this is what we see in here. The orange dots are close to the blue crosses, but we cannot recover exactly the measure nu. And when we do the same thing with respect to an optimal plane in the optimal weak problem, then we will find a measure, this one, which is just eta star, which is smaller in convex order than nu, but closer in the Wasserstein distance to mu. Maybe this does not help that much, so I'm doing another example. But I think it's kind of better. So in here I have two measures, mu and nu, supported on a spiral, okay? And I'm doing the transport between mu and nu. In this case, of course, since I have the same number of points in here, there exists an optimal Mange map, and actually the Mange map, in here I put the displacement of the measure, and I will arrive directly on the measure nu, and I will have the same displacement actually for the optimal mass transport and the optimal weak mass transport. Nice. So now if I do another example where I put more points in the measure mu, sorry. So in here I have a number of points that is proportional. I have n that is proportional to m, okay? So you know what's going to happen with the classical optimal mass transport. You will have that actually 4 or 5, I don't remember, points are going to the same point of the same support of nu. Sorry. So in here you have something that is really that is optimal when you send 4 points on 1 point, 4 points on 1 point, and you go on like this under the spiral. If you do with and in here, of course, the projection also arrives on ends up on nu. Okay. If you do that with optimal weak mass transport, what will happen actually is that we are not arriving on the measure mu exactly, but we arrive on a measure eta star that is smaller in convex order than mu, and that is supported on a spiral, but with points that are more uniformly putted on the support of the spiral. You see that in here, the points are more distant on the support, and you have, of course, a smaller result. Okay, so meaning that the optimal weak mass transport in here is smaller than the optimal transport in here. Okay, the value of the problem. Okay, so now we have this in mind. That maybe helps a little bit better to understand what is optimal weak mass transport with respect to optimal transport. I will talk a little bit about Wasserstein Barycenters that have been introduced by Olga, so that's nice. And so in here, I'll consider the formulation of Agee and Carlier in 2011, where you have a set of probability measures, nu1, nu k, and weights in the simplex, okay? And you are trying to find the measure mu that will minimize the point distance to the other measures, okay? And so I'm gonna drink a little bit. And in here I put some example where I consider four images. So the images, we say that our probability measure, we put weights 1 on the blue and 0 on the white, and then we normalize it. And so you will obtain this kind of behavior when you go from the turtle, for example, to the triangle, where the mass is moving along the support to average the shape of the shapes of the turtle and the triangle. Okay, and so we will see that actually the barycenter with respect to optimal weak mass transport does not at all behave like that. So it's really a different behavior. Although we will not average the shapes, or we will not average the probability measure, but instead we will more concentrate and recover the geometric features that are common to all of our probability measure. So this is really a different behavior depending on if we are using optimal transport or weak optimal transport. Okay, so at the beginning, why did we get interested in optimal weak mass transport? We were on this result of Alvarez Esteban and his co-author, and also Zemel and Panaretos, about what's being a barycenter, what does it mean in terms of fixed point equation and with respect to the Karcher mean, let's say. Karcher mean, it's a mean corresponding to the maps, associated to the maps. So they have a result that says that when you have a set of probability measures that are absolutely continuous, with at least one of them with bounded density, you will have that the unique barycenter, in classical sense, verifies this kind of equation. Okay? And this equation is exactly defined through the Monge map in here between the barycenter and each of the measures. Okay, this is the only thing that you need to define. The unique barycenter will be defined through this equality. And then what they did is propose an iterative procedure in order to recover such a fixed point, and they studied the convergence of this kind of this algorithm and stuff like that. So in that setting, we want to apply actually to move from classical optimal transport to optimal weak mass transport, and to see what happens. So in this case, this is a classical Wasserstein barycenter problem with the Wasserstein 2 distance and the optimal Monge map. Okay, when everything is nicely done, so we can write it like that way. And so really easily and really naturally, we will replace the Wasserstein 2 distance by the optimal weak mass transport, and we will recover in here the barycentric projection with respect to the optimal weak plane. Okay. And in this case, we can define in the same way at the Fréchet-Minier and the assertion Barycenter this objective function where we try to find a measure mu that will minimize the cost to go from mu to other measure in our set. Okay. So of course this problem admits solution. Actually, the solutions are not unique. So I'm going to present some intuition also and remarks about this kind of object. And with the proofs, but maybe we don't have to go through the proof, but just to see that it's really easy actually, and it's going really, really well. So first of all, when we have a weak barycenter of mu1 UK, and that we have another measure, mu tilde, that is smaller than mu in convex order, then this measure is also a weak barycenter. So this means that we will have a set of weak barycenter. And of course, there will be barycenter more interesting than others. For example, with that in mind, we have that a direct measure supported on the mean of the expectation will be a weak barycenter. So of course, a direct measure is not an interesting barycenter to look at, and we have lost every information about our set of measures, but they are not the only ones. So an idea of a proof, it's just you have to use actually the Strassen theorem, saying that when you have two barycenters that are in convex order, we can write it in the form of the conditional expectation. Okay, and then, well, I don't think it's really necessary, but in here you use Jensen, conditional Jensen. Then you use the particular, the actual definition of being in convex order also. And you will, the Jensen, and you will see that this measure is in convex order with nu, and you will be able to show this inequality, where you see that the optimal Weber transport between mu and nu is greater than the one between mu tilde and nu. Okay, and you do that for all of mu. You measure in your set nu1 nu k, and you will obtain, of course, that the claim that a barycenter mu tilde is also a weak barycenter. Okay, and then, since you do that with a direct measure, you can actually have directly, by solving the problem, knowing that one Dirac measure supported on one Dirac is also a weak barycenter. By resolving this problem, you will see that the barycenter is uniquely attained in the support point, this one. Okay, just to say that it's really. Really easy to obtain this kind of results. Another hint is that when you have probability measures that all have the same mean, you will have that being a weak barycenter is equivalent to being smaller in convex order than any of your measures. So this is where we can see that it's really key to have this notion of convex ordering in case of weak barycenters. Okay, I think. How would we do that actually? Since we know that a weak barycenter, the direct measure in the direct measure supported on the pondered mean of the expectation of our measure is a weak barycenter, we actually have directly the value of the objective function at its optimum value, at its optimum. Okay, and that way we can see that we'll see that all of the measures that are solving that are going to be weak barycenters. Okay, and so for Gaussian distribution, this actually means that this set of, when we have Gaussian distribution with all of the same mean, the set of Gaussian distribution with the same mean but with a variance smaller than the variance of all of the others is also a weak barycenter. Okay. Okay, and so why that? It's because actually the convex order for Gaussian distribution is known, and two Gaussian distributions are in convex order if and only if their covariance matrix is also, is the covariance matrix of the smaller one is smaller than the covariance matrix of the greater one. And so smaller in the sense of symmetric definite positive matrices. Okay. And then one last result, we can actually compare a weak barycenter with the classical notion of Wasserstein barycenter. And we realize that the distance between these two is actually controlled by the variance of each of our measures. Okay? And of course, if the variance is going to 0, if we are going to Dirac's, if all of our measures are going to Dirac, we will obtain that the classical barycenter and the weak barycenter are the same. Okay. So now, just a small result that is kind of interesting to understand why, what is the information contained in the weak barycenter. So in here we have a weak barycenter mu and x following the law of nu, and we have our set of priority measures, nu1, nu k, and with yi following the law of nu y. And so we can see that if mu is not a Dirac, we will see that each of the measures, each of the random variable yi, can be written actually as a weak barycenter plus a translation plus some noise inside this class. Okay. So meaning that when we have a weak barycenter, it's actually it can be thought of as a representation of y with a translation and some noise. So in this in mind, this is why I said we can see a weak barycenter as a measure that will keep the geometrical information common to each of the measures of the set. Okay. And again, the proof is based actually when we have this priority measure, we have a bunch of relationship between them. Relationship regarding to the convex order. And so, for example, we have xy that has the law p of mu nu. We have this equality almost surely because of the convex ordering property. And we have also this equality related to the convex ordering. And then we just write it in another way. We can recover the theorems that I've presented here. Okay. So it's really good thanks to the Strassen theorems that things are working well. Okay. Now just a small example that I put like quotation mark in here, robustness to outlier, because it's not proven in any case, but it's also a way to see this property of latent variable. So in here, I have a bunch of data. So I have, I think, 15 empirical Gaussian distribution. So I have sampled from Gaussian distribution, 15 of them, and I'm doing a barycenter. From this 15 distribution, I'm doing a barycenter, and that recovers more or less the shapes of the data. And this is really classical because thanks to also the talk of Agnès, we know that the barycenter of Gaussian distribution is still a Gaussian distribution, so we recover something that is meaningful. Now, if I consider the same set, but I randomly translate some of the data, what I recover is Otzi barycenter, the classical Wasserstein barycenter, will have outlier. And this is well known because actually optimal transport is not robust to outlier. Because if we have everything here, but at some point in here, we must move to this point. So I think it's Gabriel that presented unbalanced optimal transport. We can deal with this kind of setting. But still in here, we can see that the weak barycenter is blind to this kind of outliers. Okay, so now some fixed point approach in the same spirit of the one from Matan and his co-author. So in here we define a sequence of measure in the same fashion that for the classical transport. sequence of measure mu n plus 1, n plus 1 that is equal to g of mu n. And g is defined simply, naturally, as the push forward of mu against this pondered sum with respect to the barycentric projection computed with optimal weak plane. Okay, so this is what I've written in here. So in this case, actually, we have that mu, if mu is a weak barycenter, we will have that mu verifies this equation. And this is this confirms actually this inequality. Then you can derive the result. Okay. And this is obtained also in the classical setting where S mu nu I is a Mange map. Okay. And then we have I will talk about that just in the next slide. But of course, we don't know that if mu verifies such kind of if mu verifies such a fixed point inequality, we don't know if it's a weak barycenter actually. But this, even in a classical case, it's not that easy to have this kind of implication. So now that we have G, we have the definition of this sequence. We will have that that every converging subsequence of mu n must converge to a fixed point of G. And this is a really similar result than in the classical case. Now about the remark that I said. So in order to have the reverse implication in the classical case of optimal transport, so meaning that if I'm fixed point, then I am a Wasserstein barycenter, you will need more engaging assumption. So you will need, Inage and Carlier proved that in the paper in 2011, that you need that this fixed point equation, you need it to be true for every x in RD, not for mu almost every x, okay, which is really stronger. And another thing that has been provided in Zemel and Paneretos, by Zemel and Paneretos, by first in 1D, by assuming, well, there are several assumptions, but by assuming that the density of mu1, mu_k are bounded and strictly positive, and by assuming that if the barycenter is also bounded and strictly positive, then you will have the reverse inequality. So it's really strong assumption, and actually we don't know much about this setting of reverse inequality. So in our work, basically in here they are invoking more smoothness in order to prove this kind of reverse inequality. In our work, as it is, we don't think that we can obtain such inequality. We will need to first add more regularity and maybe other things. So it's still under study. Okay. I'm just going to talk really quickly about the streaming scenario. So what I mean by streaming is that I want to construct a barycenter. I'm receiving along the way some priority measure, and at each time that I'm receiving a priority measure, I want to construct a barycenter. Okay. So in this case, we need a larger framework, let's say, and we need to work on a space of priority measure supported on a space of priority measure with moment of order 2. So Q is a priority measure supported on P2 of RD. In here you have the definition of what we call weak optimal barycenter. And of course, if Q is discrete, meaning if Q is supported on only a finite number of priority measure, you will recover the classical definition of barycenters. And so this has been studied by Thibault and his co-author in the classical case, and also by Alvarez Esteban in 2015. So I'm not going to talk a lot about this result and this setting, but what I can say is that in the same process you have to find, you can prove a result of mu is a weak barycenter of this kind, so it minimizes this functional, then we'll have this kind of, it will verify this fixed point equation, me almost surely. And this kind of, this equation, you have to ensure yourself that actually this barycentric projection is measurable with respect to x and with respect to nu. So this is a little bit of work also. And once you have that, you also can propose an iterative procedure that will converge towards this fixed point. And an iterative procedure that I can write. Yeah. So in here you see a sequence will be defined as a projection also with a push forward. Oops, wait a minute, gamma identity. Push forward mu. And so mu n, you're receiving along the way new probability measure mu n, and you're constructing a sequence like that. Okay, and so this can be understood actually, I'm saying like, again, a relay with quotation mark, this can be understood as a stochastic gradient descent where this map, this barycentric projection, will play the role of a gradient. Okay, and this is kind of used in the classical way when you replace this map with a Monge map. In the paper from Bakov-Veragas and Iscota, where they try where they analyze actually this iterative procedure. So for their paper, they need to have also more regularity on the measures. They need to have at least absolute continuity of the measure. Okay. And in this paper, by Curie, Monod, Rigolet, and Stromé, actually they do the same thing, but in the special case of Gaussian in the Wasserstein space. So when we consider Gaussian in the Wasserstein space, this set of Gaussians, it's actually equivalent to the Bohr-Wasserstein metric, and they study the iterative procedure, and they can find in this special case bounds on the convergence, on the speed of rate of convergence of this algorithm. Okay, and to do that, they need a Polyak, the same inequality as François Xavier presented this morning, and they need to build one in order to prove the convergence result. And it's really an engaged paper, even for the Gaussian case, which is quite natural and quite simple. It's already really complicated to prove such kind of rates. Okay, so now some computational talk about how do we actually compute this weak barycenter. First of all, this weak optimal transport plan. So yeah, what we see in here is that to compute this push forward, we only need actually the barycentric projection. And for the barycentric projection, we only need the optimal weak plan in the optimal weak mass transport. So first of all, if we rewrite it as a good computation scientists that we are computed things in discrete, and we need we have two probability measures, mu and nu, supported on discrete, supported on discrete on points. And so that way we can rewrite the problem as a quadratic programming, and this you can solve it with your favorite solvers. Okay, but this is really unstable. Another way to compute, so in here you have to find the matrix of the size of the support of mu and nu, and in here it's just actually the barycentric projection. It's just the conditional expectation with these constraints. We also proposed a proximal algorithm to solve this kind of problem, where we have this first function that we want to minimize with the set of constraints. So what you do basically is just to compute the gradient of f and then to project it on G. And since G is is an indicator function, you will have that, you have the prox of G is just the projection function, and you will project on the space of good marginals, mu and nu. And recently there is a paper from Paty and his co-author with their proposed mirror descent algorithm to solve in the primal and in the dual the optimal weak mass transport. And this paper also proposed application in economics, and it's really nice. It's a really nice paper where we can understand in an economic point of view what is a optimal weak mass transport. And I also recommend it if you're interested in that. Okay, and so now some example. So in here, I have measure mu1 and mu2 in blue and orange. Well, I don't know. Yeah, blue and orange. Blue, this one, orange. And we have an OT barycenter in red and the OT barycenter in the weak barycenter in black. So you can see that behaves quite differently. And you have that this black dots, you can see that as something more concentrated in convex order. Well, if you have, first of all, the translation, you put them in the middle, and then you have something more concentrated than the other dots. And here you have something similar, where I put, on the right, where I have two probability measures in blue and orange that are supported on ellipses with noise. And what you work over with the OT bar is a circle in the middle with noise, and with the weak bar there is less noise than in the OT barycenter. But why is it smaller? It's just because you want to, since you have one ellipse in that way, one ellipse in the vertical way, you will work over something that is smaller in convex order, so something that is both included, if you can see, if you can think like that, included in the horizontal ellipse and the vertical ellipse. Okay, so maybe to have another example, still with the spiral, because I think it works quite well with spirals, where the weak barycenter is capable of recovering a better spiral shape because of this property of representing, gathering the geometric property of all of our probability measure. Okay, so yeah, more or less that's the point. So maybe I'm going to present just what we want to do after, because I think that at the end of this presentation you might be a little bit, I want to see more than just Dirac's and see more than just small examples. So first of all, of course, we want to develop this idea around probability measure that will allow us to not find the Dirac, to escape from the Dirac cases, which is not interesting. Secondly, we want to understand what is this set of weak barycenter, meaning that it is defined through the notion of convex order. And convex order, actually, we know there is a maximal element in this set of convex order. In 1D, in one dimension, it is proven. In dimensions greater than D, we don't, dimension greater than 1, we don't know what's happened. So this is also a problem to which weak barycenter should we choose to have the most information about our set of probability measure. Then, of course, naturally we can say, so since it's not symmetric, why can we not look at this kind of result, this kind of functional? So when you think about it, the way that I presented it, it's kind of, since we know that if we have the case really simple, where we have probability measure with the same mean, and we know that being a weak barycenter is equivalent to being smaller in convex order than other of the measure in our data set, we can see that as maybe like, I don't know how to say it in English, but PGCD, PGD, like greater common divisor, something like that. And in the other way, why not seeing that as a PPCM, greater common multiplier, if you want to, something like that. Okay, so what does it mean in this case to have to be bigger in convex order than all of the other measures? And then, in order to maybe to tackle the Dirac cases, why not adding some entropy at the functional in order to obtain weak Barycenter, sorry, that is more spread out, let's say, than a Dirac, and maybe is the most spread out correspond to the greater in convex order, for example. So these are all the questions that we are interested in at the moment. Okay, and to just, okay, there is a bunch of paper, but more or less, if you're interested in application, you should see, it's not rated in here, so one from Patty, application in economy, and if you want to just know what's optimal weak mass transport, like the main theorem and stuff like that, and you can see this one where they prove existence, duality, cyclical monotonicity, that are really classical theory around optimal transport that are put into the place of optimal weak mass transport. That's it. Thank you.